Picture this, a world where the night sky holds a glowing orb, silent and still, yet hiding a secret that has baffled scientists for decades. The Moon, our closest cosmic neighbor, has a magnetic mystery that defies everything we know about how planets and moons should behave. Right now, the Moon barely has a magnetic field to speak of, a ghost of what Earth's powerful shield looks like. But here's the twist. Buried in its ancient rocks are clues that tell a different story. Billions of years ago, the Moon may have had a magnetic field strong enough to rival Earth's. So what happened? How did it vanish, leaving behind only whispers of its past? This isn't just a scientific curiosity. It's a puzzle that could rewrite our understanding of how worlds evolve and why some thrive while others fade. Stick around, because by the end of this video, you'll see the Moon in a whole new light. And who knows, you might just crack the mystery yourself. Now let's zoom in on the Moon as it is today. Unlike Earth, with its powerful magnetic shield that deflects solar winds and protects life, the Moon's magnetic presence is barely a whisper. Earth's field is like a roaring engine, generated by the churning molten metal in its core. But the Moon, it's more like a flickering candle with only faint traces of magnetism scattered across its surface. Here's where it gets interesting. While the Moon lacks a global magnetic field, it's not completely silent. Satellite missions and studies of lunar rocks have uncovered something unexpected: pockets of magnetism, like invisible scars etched into the crust. These anomalies are strongest in certain regions, almost as if the Moon is hiding fragments of its past beneath the dust. What's even more puzzling is how these magnetic patches don't follow any clear pattern. Some are near ancient lava plains, others near massive impact craters, suggesting that the Moon's magnetic history isn't just a simple story of fading away. It's a patchwork of events, each leaving behind clues that scientists are still piecing together. So why does this matter? Because these weak, scattered fields are like breadcrumbs leading us back to a time when the Moon may have been far more dynamic than it appears today. And that's a mystery worth unraveling. Here's something that might surprise you. Those faint magnetic whispers on the Moon today, they're just the echoes of something far more powerful. The real breakthrough in unraveling this mystery came from the Apollo missions, when astronauts brought back pieces of the Moon itself. Hidden inside those rocks was a secret traces of an ancient magnetic field frozen in time. Scientists analyzing these samples made a stunning discovery. Some of the rocks were magnetized, as if they'd been exposed to a strong magnetic field when they formed billions of years ago. Think of it like finding an old compass needle still pointing north long after the magnet is gone. That's what these lunar rocks were doing, preserving a record of the Moon's magnetic past. The strength of this ancient field is what really baffles researchers. Based on the magnetism locked in those rocks, the Moon's field might have once been as strong as Earth's is today. That's a huge deal, because it means the Moon wasn't always the quiet, geologically dead place we see now. It had a dynamic interior, possibly even a molten core churning away like Earth. But here's the twist: this magnetic field didn't last. By around 1 billion years after the Moon formed, the evidence suggests it had faded dramatically. So what happened? Did the Moon's core cool down too fast? Was there some catastrophic event that shut it off? These are the questions that keep scientists digging deeper into those precious Apollo samples, because every clue brings us closer to understanding how our closest cosmic neighbor once worked. And if you think that's fascinating, just wait until we explore how something as violent as an asteroid impact could have left its own magnetic mark on the Moon. That's a story for another section. Now, let's piece together one of the most compelling explanations for the Moon's ancient magnetic field, the Dynamo Theory. Picture Earth's magnetic field, that invisible shield protecting us from solar radiation. It's generated by a churning, molten core acting like a giant electromagnet. Scientists believe the moon might have once worked the same way. Here's how it would have happened. For a dynamo to exist, the moon needed three key ingredients: a molten metallic core, rapid rotation, and vigorous convection. Think of it like stirring a pot of soup to keep it hot. The molten iron in the core would have swirled, creating electric currents, and those currents would have generated a magnetic field stretching far into space. But there's a catch. The moon is small, just a quarter of Earth's width, and that tiny size makes sustaining a dynamo tricky. Smaller bodies lose heat faster, so a molten core would cool quickly. Plus, the moon's rotation is slow now, but back then, it might have spun much faster, giving that dynamo the motion it needed to kickstart. The real puzzle. Timing. The dynamo theory suggests the moon's magnetic field should have faded as its core cooled, matching the evidence from those Apollo rocks, but some details don't add up. For instance, why did the field last as long as it did? And how could such a small body maintain a field as strong as Earth's, even temporarily? This is where the debate heats up. Some researchers argue the dynamo alone can't explain everything, leading us to other wild possibilities like whether colossal asteroid impacts could have given the moon a magnetic jolt. But that's a story for another moment. For now, the dynamo theory remains the leading contender, a reminder that even our closest cosmic neighbor still holds secrets waiting to be unlocked. Now, let's tackle the big question: why does the dynamo theory leave some scientists scratching their heads? The moon's small size is the first hurdle. Imagine trying to keep a cup of coffee hot versus a giant pot. The smaller it is, the faster it cools. The moon's core, once molten, would have lost heat quickly, making it tough to sustain a magnetic dynamo for long. Then there's rotation. Today, the moon turns slowly, but even in its youth, it might not have spun fast enough to keep that core churning vigorously. Without that motion, the dynamo effect weakens or stops altogether. Some models suggest the moon's early rotation could have been just enough to kickstart a magnetic field, but maintaining it for billions of years. That's where the math gets shaky, but here's where it gets interesting. If the dynamo theory doesn't fully explain the moon's magnetic past, what else could? Enter asteroid impacts. Picture a massive rock slamming into the moon, unleashing enough energy to temporarily melt parts of the crust. That chaos could generate short-lived magnetic fields, imprinting their signature on lunar rocks without needing a long-lived dynamo. Some researchers even point to the moon's early volcanic activity. Lava flows carrying magnetic minerals could have solidified in the presence of weaker magnetic fields, creating localized anomalies we see today. It's like freezing a snapshot of magnetism in time. The debate isn't settled, and that's the beauty of science. Every new mission, every fresh analysis brings us closer to unraveling the moon's magnetic mystery. Whether it's a faltering dynamo, colossal impacts, or something entirely unexpected, one thing's clear: the moon still has stories to tell. And speaking of surprises, let's turn our attention to another fascinating possibility: how those asteroid impacts might have given the moon a magnetic jolt. Now, let's dive deeper into this idea of asteroid impacts leaving their magnetic mark. Picture a colossal space rock, miles wide, crashing into the moon at unimaginable speeds. The energy released wouldn't just carve out a crater. It would superheat the surrounding rock, turning it into a swirling, molten soup. In that chaos, something remarkable could happen. As the impact melts the lunar crust, charged particles within the molten material start moving freely. If even a faint magnetic field were present, say, from the solar wind or a waning lunar dynamo, those particles could align like tiny compass needles, locking in a magnetic signature as the rock cools. This process, called shock-remnant magnetization, might explain why some lunar regions have strong magnetic patches while others don't. But here's the twist. Not all impacts would create the same effect. The angle, speed, and size of the asteroid matter. A direct high-energy hit could generate a stronger temporary field, while a glancing blow might leave little trace. Scientists studying lunar meteorites fragments ejected by impacts have found some with surprising magnetic strength backing this idea. Then there's timing. If impacts happened during periods when the moon still had a weak global field, even briefly, the combined effect could amplify the magnetization. It's like stamping a fading signal into the rock before it disappears entirely. Some of the moon's most puzzling magnetic anomalies, like those near giant basins, might be scars from these ancient collisions. Of course, this isn't a perfect solution. Critics point out that not all impact sites show strong magnetism, and the math on how long these fields could last is still being debated. But it's a compelling piece of the puzzle, showing how violence and chaos might have shaped the moon's hidden magnetic history. And as we'll see next, these impacts could tie into an even bigger story, the moon's fiery birth itself. Now, let's take a step back, way back to the very beginning of the moon's story. Imagine a time when Earth was young, and a Mars-sized object, often called Theia, slammed into our planet in a cataclysmic collision. This violent event didn't just reshape Earth, it flung molten debris into orbit, which eventually coalesced into the moon we know today. But here's where things get even more fascinating. Could this colossal impact have also kick-started the moon's magnetic field? The energy from that collision would have been unimaginable, heating the moon's early core to extreme temperatures. A molten, swirling core is one of the key ingredients for a magnetic dynamo, the same process that powers Earth's magnetic field today. Some scientists argue that the sheer force of the impact could have set the moon's core into a temporary frenzy, creating a short-lived but intense magnetic field in its earliest days. But there's a catch. For a dynamo to last, the core needs to keep churning, and the moon's small size works against it. Unlike Earth, the moon would have cooled rapidly, shutting down any dynamo activity relatively quickly. Yet, lunar rocks tell us the magnetic field persisted for hundreds of millions of years after the moon formed. So how do we square that circle? One possibility is that the giant impact left the moon's core in a state of turbulent motion, prolonging the dynamo's life. Another theory suggests that tidal forces from Earth stretching and squeezing the moon's interior could have kept the core active longer than expected. It's like stirring a cup of coffee to keep it warm, but on a planetary scale, of course, not everyone agrees. Critics point out that even with these mechanisms, the moon's dynamo should have fizzled out much sooner. This debate is far from settled, but what's clear is that the moon's birth and its magnetic history are deeply intertwined. The same violence that created our lunar companion might have also given it a fleeting magnetic heartbeat, one that left behind clues we're still deciphering today. And as we'll see next, understanding the moon's core composition could hold the key to unlocking this mystery even further. Now, let's dig deeper into the heart of the moon itself, its core. Understanding what's inside our lunar neighbor is crucial for piecing together the magnetic puzzle. So, what do we actually know about the moon's core? Thanks to seismic data from the Apollo missions, we've got some surprising clues. The moon's core is much smaller than Earth's, roughly 1/5 of its total radius. That's like comparing a pebble to a golf ball. Scientists believe it's made up of two layers, a solid inner core and a fluid outer core, similar to Earth's but on a much smaller scale. The outer core is likely a mix of iron and sulfur, which lowers its melting point, keeping it liquid longer than if it were pure iron. This detail matters because a liquid outer core is essential for generating a magnetic field. But here's the twist. The Apollo seismometers detected moonquakes, and their patterns suggest the core isn't entirely molten today. Some researchers think the outer core might have partially solidified over time, which would explain why the moon's dynamo eventually sputtered out. Yet the fact that it was ever active at all raises bigger questions. How did such a small core sustain a magnetic field for so long? One theory points to the moon's early chemistry. If the core had just the right mix of lighter elements like sulfur, it could have stayed molten for hundreds of millions of years, even as the moon cooled. Another idea involves heat from radioactive elements in the mantle, providing extra energy to keep the core churning. The Apollo data also revealed something unexpected. The moon's core might be slightly offset from its center. This misalignment could have created uneven forces, stirring the core in ways that prolonged the dynamo's life. It's like tilting a spinning top. The wobble introduces new motion. Of course, not all the pieces fit neatly. Some models struggle to explain how the core retained enough heat and motion to sustain a magnetic field for as long as the rocks suggest. That's where future missions come in with better instruments. We might finally get a clearer picture of what's really going on beneath the lunar surface. And speaking of new discoveries, modern missions are building on Apollo's legacy, uncovering even more clues about the moon's magnetic past, but that's a story for another moment. Now, let's turn our attention to the fascinating field of paleomagnetism, where scientists unlock secrets hidden in lunar rocks. Imagine these rocks as tiny time capsules, preserving clues about the moon's magnetic past. By studying their ancient magnetic signatures, researchers can piece together a timeline of when and how strong the moon's magnetic field once was. Here's how it works. When molten rock cools, minerals within it align with the surrounding magnetic field, essentially freezing that direction and strength into the rock. It's like a snapshot of the magnetic conditions at that moment in time. Lunar samples brought back by the Apollo missions contain these magnetic imprints, allowing scientists to measure their orientation and intensity. But it's not as simple as reading a compass. These rocks have endured billions of years of space weathering, impacts, and temperature changes, which can scramble their magnetic signals. To filter out the noise, researchers use precise lab techniques, like heating the samples in controlled environments or exposing them to alternating magnetic fields. This helps isolate the original magnetic signature from later distortions. What's truly remarkable is what these studies have revealed. Some lunar rocks show evidence of a surprisingly strong magnetic field, comparable to Earth's today around 3.5 billion years ago. That's long after the moon's formation, challenging earlier assumptions that its dynamo should have faded quickly. Other rocks tell a different story, with weaker or even absent magnetism, hinting at periods when the field fluctuated or collapsed entirely. These inconsistencies have sparked debates. Could the moon's dynamo have turned on and off in cycles, or were some rocks magnetized by other forces like asteroid impacts? Paleomagnetism doesn't just give us answers, it raises new questions, pushing scientists to refine their models of the moon's core and magnetic history. And with each new lunar sample analyzed, whether from past missions or future ones, we get closer to solving this cosmic puzzle. The rocks may be silent, but their magnetic whispers are speaking volumes. Shifting our gaze from ancient rocks to cutting-edge technology, let's explore how NASA's ARTEMIS mission is revolutionizing our understanding of the moon's magnetic quirks. Unlike the Apollo missions, which brought back physical samples, ARTEMIS is a pair of orbiting spacecraft designed to study the moon's magnetic environment in real time, painting a dynamic picture of its present-day anomalies. These twin probes, originally part of the ARTEMIS mission studying Earth's auroras, were repurposed to scrutinize the moon. Equipped with ultra-sensitive magnetometers, they've been mapping the strength and direction of magnetic fields across the lunar surface with precision never before achieved. What makes ARTEMIS special is its ability to detect subtle variations in these fields, even in regions where traditional measurements might miss them. One of the mission's standout discoveries involves the moon's mysterious magnetic bubbles. These are localized pockets where the magnetic field is unexpectedly strong, often shielding patches of the surface from the solar wind. ARTEMIS has revealed that these bubbles aren't static, they shift and interact with charged particles from the sun, creating miniature protective zones. This finding has huge implications, suggesting that future lunar explorers might use these natural shields for protection against radiation. But the surprises don't stop there. By comparing ARTEMIS data with older maps, scientists have noticed that some magnetic hotspots align perfectly with ancient lava flows. This hints that volcanic activity billions of years ago could have left behind magnetized minerals, freezing the field's direction into the crust. Other anomalies, though, defy easy explanation, like the Lunar Gamma Swirl, a bright, swirling pattern with an intense magnetic signature that doesn't match any known geological feature. Perhaps most intriguing is how ARTEMIS has deepened the dynamo debate. While some anomalies support the idea of an ancient global field, others appear too scattered or intense to fit the model neatly. Could impacts or tidal forces have played a bigger role than we thought? Every new data point from ARTEMIS adds another piece to this cosmic jigsaw, proving that the Moon's magnetic story is far from over. As these probes continue their silent dance around the Moon, they're not just collecting data, they're rewriting the textbook on lunar magnetism, one orbit at a time. And with each pass, we inch closer to unraveling one of space's most enduring puzzles. Now, let's turn our attention to another key player in lunar exploration, China's Chang'e missions. While NASA ARTEMIS probes orbit the Moon, China has been making groundbreaking strides with its own lunar program, offering fresh perspectives on the Moon's magnetic mysteries. The Chang'e missions, named after the mythical Chinese moon goddess, have been quietly transforming our understanding of lunar magnetism. Chang'e 1 and 2, launched in 2007 and 2010, were the pioneers, mapping the Moon's surface and magnetic environment with unprecedented detail. But it was Chang'e 3, landing in 2013, that marked a major leap. It became the first spacecraft to soft land on the Moon since the Soviet Union's Luna 24 in 1976. Equipped with advanced magnetometers, Chang'e 3 measured the magnetic field directly at the surface, something orbiters like ARTEMIS can't do. These ground-level readings revealed surprising variations, showing how localized magnetic anomalies can differ dramatically even over short distances. One striking discovery was that some regions had magnetic fields 10 times stronger than expected, challenging earlier assumptions about how these features form. Then came Chang'e 4, which made history by landing on the far side of the Moon in 2019, a first for any mission. Its instruments detected magnetic fluctuations tied to solar-wind interactions, providing clues about how the Moon's lack of a global field affects its surface environment. The rover U-22 even found evidence of magnetized minerals in the soil, supporting theories that ancient volcanic activity or impacts left behind these magnetic fingerprints. But perhaps the most exciting data comes from Chang'e 5, which returned lunar samples to Earth in 2020. By studying these rocks alongside magnetic measurements, scientists are piecing together how the Moon's magnetic history aligns with its geological timeline. Early analyses suggest some samples carry traces of a time when the Moon's dynamo was still active, offering tantalizing hints about when and why it shut down. China's missions complement NASA findings, filling gaps in our knowledge with ground truth measurements and fresh samples. Together, they're painting a fuller picture of the Moon's magnetic past, one that's far more complex than anyone imagined. As Chang'e 6 and future missions prepare to launch, we can expect even more surprises, bringing us closer to solving this celestial puzzle. Up next, we'll explore how the solar wind, that relentless stream of charged particles from the Sun, shapes the Moon's remnant magnetic fields in ways we're only beginning to understand. Now, let's shift our gaze to the Sun's invisible hand in this lunar mystery. The solar wind, that constant stream of charged particles racing from the Sun at nearly 1 million miles per hour, has been sculpting the Moon's magnetic landscape for billions of years. Without a global magnetic field to deflect these particles, the Moon's surface has been exposed to this relentless cosmic weather, leaving behind fascinating clues in its magnetic fingerprints. Here's how it works. When the solar wind slams into the moon, its high-energy particles interact with the surface in surprising ways. In areas where the moon still has localized magnetic fields, these pockets act like miniature shields, bending the solar wind around them. This creates what scientists call mini magnetospheres, tiny bubbles of protection where the surface weathers space differently than its surroundings. Over time, these interactions leave distinct patterns. Some regions get bombarded more heavily, while others remain relatively untouched, but the solar wind doesn't just bounce off. Some particles get trapped in the moon's soil, subtly altering its magnetic properties. Experiments with lunar samples show that prolonged exposure to the solar wind can even magnetize certain minerals, creating weak but detectable fields. This might explain why some areas, like those studied by China's Chang'e missions, show unexpected magnetic strength despite the moon's overall weak field. The most dramatic effects are seen in the moon's magnetic anomalies, those puzzling patches where the field is oddly strong. Some researchers think these could be solar wind archives, preserving records of ancient magnetic activity. When the moon's dynamo was still active, its global field may have redirected the solar wind in ways that left permanent marks on the crust. Now, billions of years later, these anomalies are like time capsules, holding secrets about the sun's past behavior and the moon's magnetic youth. Interestingly, the solar wind might also help explain those mysterious bright swirls on the moon's surface, like Lunar Gamma. One theory suggests that as the solar wind particles are deflected by magnetic anomalies, they selectively darken or lighten the soil, creating those eye-catching patterns. It's a cosmic art project painted by charged particles over eons. As we piece together this puzzle, one thing becomes clear: the solar wind isn't just a background player. It's an active sculptor, shaping the moon's magnetic legacy in ways we're only starting to decode. Next, we'll zoom in on those enigmatic lunar swirls and the magnetic signatures that make them some of the moon's most captivating mysteries. Now, let's turn our attention to one of the moon's most visually striking mysteries, those bright, swirling patterns that dance across its surface like cosmic brushstrokes. These lunar swirls, often stretching for miles, aren't just beautiful oddities. They're deeply connected to the moon's magnetic anomalies, creating a puzzle that scientists are still untangling. Take Lunar Gamma, the most famous of these swirls. From orbit, it looks like a pale, twisting ribbon against the darker lunar soil. But here's the twist: right beneath it lies one of the moon's strongest localized magnetic fields. That's no coincidence. Researchers believe the magnetic anomaly deflects the solar wind, shielding the surface underneath from the constant bombardment of charged particles that darken the surrounding terrain. Over time, this creates a stark contrast, leaving the protected area brighter and smoother, while the exposed soil weathers and darkens. But not all swirls fit this neat explanation. Some appear where magnetic fields are weaker or don't align perfectly with the anomalies. This has led to other theories, like the idea that comet impacts could have vaporized surface material, leaving behind these bright trails. Others suggest electrostatic forces stirred up by the solar wind might be lifting and sorting fine dust particles to form the patterns. What makes these swirls even more intriguing is their potential to unlock secrets about the moon's past. If magnetic anomalies are indeed shielding them, that implies the anomalies have been stable for eons, long enough to preserve these delicate features. That's a big clue about the durability of the moon's crustal magnetism, and whether it's tied to ancient volcanic activity, impacts, or even a long-lost dynamo. Up next, we'll zero in on Lunar Gamma itself, a swirl so enigmatic it's become the poster child for lunar magnetic mysteries. What makes it stand out, and why does it defy so many of our expectations? The answers might rewrite what we know about the moon's hidden magnetic life. Now, let's unravel the mystery of Lunar Gamma, the moon's most iconic swirl. This dazzling feature isn't just a visual marvel, it's a scientific head-scratcher. Unlike other lunar swirls, Lunar Gamma boasts an unusually strong magnetic signature, yet it refuses to fit neatly into any existing theory. For starters, its magnetic field is oddly lopsided. While most lunar magnetic anomalies are patchy, Lunar Gamma's is concentrated and asymmetrical, as if something beneath the surface is distorting it. This has led some researchers to suspect buried metallic deposits, perhaps remnants of a colossal asteroid impact that never fully melted into the moon's crust. Others argue the swirls shape a graceful, elongated curve hints at ancient lava flows magnetizing the terrain as they cooled. But here's where it gets weirder. Lunar Gamma's magnetic field is strong enough to deflect the solar wind, yet it doesn't perfectly align with the bright swirl above it. Parts of the swirl spill beyond the magnetic shield, while some shielded areas remain dark. This mismatch has scientists questioning whether magnetism alone can explain its formation. Could electrostatic forces or even mini-meteorite impacts be enhancing the effect? Then there's the age puzzle. Lunar Gamma's crisp, well-preserved edges suggest it's relatively young, geologically speaking. But if the magnetic anomaly protecting it is ancient, how has the swirl stayed so pristine? Some propose the anomaly is actively renewing itself, perhaps through lingering heat in the moon's crust or residual currents in conductive materials below. What's clear is that Lunar Gamma challenges our understanding of lunar magnetism. It's a reminder that the moon still holds surprises, and that solving one mystery often reveals another. Up next, we'll explore how volcanic activity might have shaped the moon's magnetic story, adding yet another layer to this cosmic puzzle. Now, shifting our gaze beneath the moon's surface, let's dig into the fiery possibility of volcanic activity shaping its magnetic past. While the moon today is a quiet, cratered world, billions of years ago, it was a hotspot of volcanic eruptions. Vast lava plains like the dark patches we see today, known as Maria, were once rivers of molten rock. But could these ancient eruptions have left behind more than just scars? Some scientists think they might hold the key to the moon's magnetic enigma. Here's the intriguing part. When lava rich in iron cools, it can lock in traces of the surrounding magnetic field, much like a snapshot. Apollo missions brought back samples of these volcanic rocks, and many carried strong magnetic imprints, suggesting they solidified in the presence of a robust field. But was this field generated by the moon's core, or could the volcanoes themselves have played a role? One theory proposes that as lunar lava flows cooled unevenly, they created localized magnetic zones like invisible fingerprints scattered across the surface. Yet there's a twist. For volcanism to produce widespread magnetism, you'd need enormous, sustained eruptions. While the moon's Maria are vast, they're not evenly magnetized, leaving gaps in the story. Some researchers argue that volcanic activity might have supercharged an existing dynamo, temporarily amplifying the moon's magnetic field during peak eruptions. Others point to smaller-scale processes, like gas-rich lava fountains spraying charged particles that could have induced fleeting magnetic patches as they settled. The plot thickens when we consider timing. Lunar volcanism peaked around 3 to 4 billion years ago, roughly the same window when the moon's dynamo is thought to have faded. Could the two events be linked? Did the cooling of the moon's interior, which eventually shut down its core dynamo, also trigger one last volcanic hurrah, leaving behind these magnetic clues? What's certain is that the moon's volcanic past adds a compelling layer to the mystery. It's a reminder that magnetism isn't just about what happens deep inside a planet. Sometimes the answers might be written in stone, quite literally on the surface. Next up, we'll examine how Earth's gravitational pull might have stirred the moon's core, adding yet another piece to this cosmic puzzle. Now, let's turn our attention to an invisible force that might have played a hidden role in the moon's magnetic story, Earth's gravitational pull. Just as the moon tugs on our oceans to create tides, Earth's gravity has been stretching and squeezing the moon for billions of years. But this tidal force didn't just shape the moon's surface, it could have stirred its molten core too. Here's how it works. Imagine a ball of molten metal, slightly squished and stretched by a nearby giant. That constant kneading would keep the liquid churning, much like swirling a spoon in a cup of coffee. If the moon's core was once fluid and active, these tidal forces could have boosted convection, the movement of hot, buoyant material rising and cooler material sinking. And convection is the engine that powers planetary dynamos, including Earth's magnetic field. The timing fits. Early in the moon's history, it orbited much closer to Earth, meaning tidal forces were far stronger. Some models suggest this gravitational tug-of-war might have revved up the moon's core dynamo, giving it a temporary magnetic boost. But as the moon gradually drifted outward, Earth's grip weakened and the dynamo could have sputtered out. There's a catch, though. The moon's core is small, about 1/5 the size of Earth's, and today it's mostly solid. For tidal heating to work, the core would have needed to stay molten long enough for these forces to matter. Some scientists argue that radioactive elements decaying in the core could have provided extra heat, keeping it fluid longer. Others think tidal forces alone weren't enough and point back to impacts or volcanism as the real drivers. What's fascinating is that this isn't just a moon puzzle. Tidal heating shapes worlds across the solar system. Just look at Jupiter's moon Io, where gravitational flexing fuels violent volcanoes. If Earth's tides did stir the moon's core, it would show how interconnected planetary systems can be, with one world's gravity leaving a lasting mark on another. Up next, we'll zoom out and compare the moon's magnetic past with other celestial bodies. Could Mars or Mercury hold clues to solving this lunar mystery? Stay tuned. To uncover more clues about the moon's magnetic mystery, let's take a cosmic road trip and see how our lunar neighbor stacks up against other worlds. Mars and Mercury, two planets with their own magnetic tails, might hold surprising parallels or stark contrasts that shed light on why the moon's story is so unique. First, consider Mars. Billions of years ago, the red planet likely had a global magnetic field, much like early Earth. Evidence from Martian meteorites and rover data suggests this field vanished around the same time Mars lost much of its atmosphere. Scientists think Mars' dynamo shut down as its core cooled and solidified, a fate that might mirror the moon's, but with a twist. Mars is larger than the moon, so its core should have stayed hot longer. Yet both worlds lost their magnetic shields, hinting that size alone doesn't guarantee a lasting dynamo. Now zoom in on Mercury. Despite being the solar system's smallest planet, it still has a weak global magnetic field today. How Mercury's core is unusually large relative to its size, and it may contain just enough liquid metal to keep a modest dynamo churning. Unlike the moon, Mercury's magnetic field didn't fade entirely, suggesting that core composition and structure play starring roles in these cosmic dramas. Here's the puzzle. If Mercury, smaller than Mars, can sustain a magnetic field while the moon and Mars could not, what's the missing piece? One theory points to orbital dynamics. Mercury's elongated path around the Sun subjects it to intense tidal stretching, possibly keeping its core stirred. The Moon, meanwhile, might have needed Earth's early gravitational pull plus another energy source like impacts to jumpstart its dynamo. Comparing these worlds reveals a golden rule in planetary science. There's no one-size-fits-all recipe for magnetic fields. Factors like core size, composition, orbit, and even catastrophic collisions weave together in ways we're still untangling. Up next, we'll explore why some scientists think the moon's dynamo didn't just fade, it might have failed entirely. What could have caused this cosmic power outage? The answer might lie deep beneath the lunar surface. Now, let's dig deeper into one of the most puzzling questions about the moon's magnetic history. Why did its dynamo shut down so early, leaving behind only faint whispers of its once powerful field? The answer might lie in a series of cosmic misfortunes that starved the moon's core of the energy it needed to keep generating magnetism. Picture the moon's core like a spinning top. For a dynamo to work, it needs two things: a liquid, electrically conductive layer and enough motion to stir that layer into a magnetic frenzy. Early on, the moon likely had both. But as time passed, its small size became its downfall. Unlike Earth, whose massive core stays hot and churning thanks to radioactive decay and leftover heat from its formation, the moon's core cooled rapidly. Without enough internal fuel to keep the molten metal moving, the dynamo sputtered out like a dying engine. But here's where it gets even more intriguing. Some scientists argue the moon's dynamo didn't just fade quietly. It might have been snuffed out prematurely by a dramatic shift in its orbit. Billions of years ago, the moon was much closer to Earth, and our planet's gravitational pull stretched and squeezed its interior, generating heat through tidal friction. As the moon drifted farther away, that heating effect weakened, robbing the core of a critical energy source. It's like unplugging a blender mid-spin. The dynamo lost its extra kick and ground to a halt. Then there's the impact theory. The young moon was bombarded by asteroids, some so colossal they could have superheated the crust and mantle, temporarily jump-starting magnetism. But these were short-lived bursts, not a sustained dynamo. Over time, as impacts became less frequent, the moon's core cooled beyond the point of recovery. What's fascinating is that these failed dynamo scenarios aren't just about the moon. They're clues to how other small worlds lose their magnetic shields. Whether it's rapid cooling, orbital changes, or a lack of internal fuel, the moon's story reminds us that magnetism is a fragile cosmic phenomenon. And as we'll see next, modern missions are piecing together this puzzle by studying the very rocks that witnessed this magnetic collapse firsthand. Now, let's step into the digital realm where scientists recreate the moon's magnetic past, not with rocks or spacecraft, but with lines of code. Numerical simulations are like virtual time machines, allowing researchers to tweak variables and watch how the moon's core might have behaved billions of years ago. These computer models take everything we know, the moon's size, composition, and even ancient impact records, and run countless scenarios to see which ones could explain its magnetic mysteries. One key challenge: simulating a dynamo in a world as small as the moon. Earth's dynamo is easier to model. It's big, it's active, and it's right under our feet. But the moon's core was a fainter, more fragile system. To crack this, scientists feed data into supercomputers, adjusting factors like core temperature, rotation speed, and even the tug of Earth's gravity. Some simulations suggest the moon's dynamo could have flickered on and off like a faulty light bulb, while others show it might have died abruptly once the core cooled past a critical point. Then there's the impact angle. Models can recreate asteroid strikes with terrifying precision, calculating how a colossal collision might have heated the moon's crust or jolted its core. Some simulations reveal that certain impacts could have generated temporary magnetic fields like a cosmic defibrillator shocking a stalled heart. But here's the catch: these magnetic bursts would fade fast, leaving behind the patchy anomalies we see today. What's remarkable is how these digital experiments bridge theory and reality. When a simulation matches the magnetism found in Apollo-era rocks, it's like finding a missing puzzle piece. And with each upgrade in computing power, these models get sharper, helping us test wilder ideas, like whether the moon's dynamo could ever reboot, or if its magnetic scars hide clues about Earth's own ancient field. Up next, we'll see how these virtual insights are guiding real-world missions, as new lunar explorers target magnetic hotspots to confirm what simulations predict. Turning from digital simulations to real-world exploration, the next chapter in unraveling the moon's magnetic secrets is already taking shape on launch pads and in mission control rooms. NASA's upcoming Lunar Vertex mission is a prime example, designed to land a rover right on top of one of the moon's most puzzling magnetic hotspots, the Lunar Gamma Swirl. This isn't just about mapping anomalies from orbit anymore. For the first time, scientists will get ground-level data, with drills probing the lunar soil and sensors measuring magnetic fields in exquisite detail. But Lunar Vertex isn't flying solo. It's part of a new wave of missions like Japan's SLIM and India's Chandrayaan-4 that are turning the moon into a bustling scientific lab. These missions share a common goal: to test whether the simulations we just discussed hold up in the harsh light of reality. For instance, if Lunar Vertex finds that Lunar Gamma's magnetism matches the predictions of impact-induced models, it could rewrite textbooks. Or if the data points to ancient volcanic activity instead, that's a whole new mystery to solve. Then there's the long game. Future missions, like those planned under NASA Artemis program, aim to deploy networks of magnetic sensors across the moon's surface. Imagine a web of instruments working together, tracking how solar wind interacts with local magnetic fields in real time. This could finally answer whether those fields are strong enough to shield future lunar bases from radiation, a make-or-break question for human settlement. And let's not forget the commercial players. Companies like Astrobotic are developing landers capable of ferrying compact magnetometers to unexplored regions, turning every delivery into a potential scientific breakthrough. The message is clear: the moon's magnetic enigma isn't just academic. It's a puzzle with stakes for exploration, for resources, and for understanding our own planet's past. Up next, we'll zoom out to see how these magnetic quirks could shape humanity's future on the moon, from radiation shielding to mining operations. The story isn't just about what happened billions of years ago, it's about what happens next. Now, let's shift our gaze to the practical side of this lunar mystery: how these magnetic quirks could shape humanity's future on the moon. Picture a lunar base, its domes and solar panels stretching across the dusty surface. One of the biggest threats to astronauts there isn't the lack of air or water, it's radiation. Without Earth's thick atmosphere and global magnetic field, the moon's surface is bombarded by solar and cosmic radiation. But here's where those leftover magnetic anomalies might come to the rescue. Scientists are studying whether these localized fields could act as natural shields, deflecting harmful particles away from habitats. Imagine setting up camp near a magnetic hotspot like Lunar Gamma. It might offer a safer haven, reducing the need for bulky, energy-hungry shielding. Early data suggests even weak fields could scatter lower energy particles, though they'd struggle against the most intense cosmic rays. Still, every bit of protection counts when you're living on an airless rock. Then there's navigation. Unlike Earth, the moon doesn't have a consistent magnetic field to guide compasses, but those patchy anomalies, they could serve as cosmic landmarks. Future rovers might rely on magnetic maps to find their way, using these natural signposts to avoid getting lost in the monotonous lunar terrain. Some researchers even propose using artificial magnetic beacons, inspired by the moon's own oddities, to create a reliable positioning system. But it's not all upside. These same magnetic fields could wreak havoc on sensitive equipment. Dust charged by solar wind might cling to surfaces near anomalies, clogging machinery or scratching visors. Communication signals could get scrambled as they pass through magnetized zones. Engineers will need to account for these quirks when designing everything from power grids to scientific instruments. The bottom line: the moon's magnetic ghosts aren't just relics of the past, they're active players in humanity's next chapter. Whether they become allies or obstacles depends on how well we unravel their secrets. And with missions like Lunar Vertex leading the charge, we're one step closer to turning these puzzles into solutions. Next up, we'll dig into an even more tantalizing question: could these magnetic hotspots be hiding valuable resources beneath the surface? The answer might surprise you. Now, let's uncover another layer of this magnetic puzzle: how the moon's hidden fields might lead us to its buried treasures. Those mysterious magnetic anomalies aren't just curiosities for scientists. They could be treasure maps pointing to resources vital for future lunar settlers. Take metallic minerals, for instance. Some of the Moon's strongest magnetic patches overlap with regions rich in iron and titanium. These metals, forged by ancient volcanic activity or even asteroid impacts, might be concentrated where magnetism lingers. Future miners could use magnetic surveys to pinpoint the most promising spots, saving time and energy in the hunt for materials needed to build habitats or spacecraft. Then there's water ice, the holy grail of lunar exploration. Buried in permanently shadowed craters near the poles, this ice could quench thirst, fuel rockets, and even grow crops. But how do magnetic fields fit in? Some studies suggest that certain anomalies might mark areas where solar wind packed with hydrogen interacted with the soil, creating water molecules over billions of years. While the link isn't yet proven, mapping magnetism could help narrow the search for these icy deposits. Of course, it's not as simple as following a magnetic signal straight to a gold mine. Lunar geology is messy, and magnetism alone won't guarantee a jackpot. But combined with other tools like radar or spectrometers, these invisible clues could slash the cost and risk of resource hunting. Imagine a rover scanning magnetic hotspots, then drilling just meters away to strike a vein of water-rich soil. It's the kind of efficiency that could make lunar bases sustainable. The bigger picture, the Moon's magnetic fingerprints might hold keys to both its past and our future. Whether they guide us to metals, water, or even unexpected surprises, one thing's clear: these ghostly fields are far more than scientific relics. They're potential game changers in humanity's quest to thrive beyond Earth. Up next, we'll step into the debate arena where scientists clash over competing theories about the Moon's magnetic origins. Prepare for some cosmic controversy. Now, let's dive into the scientific arena where theories collide and debates heat up over the Moon's magnetic mysteries. Not all researchers agree on how our lunar neighbor once generated a magnetic field or why it faded away. The dynamo theory, which suggests a molten core once churned inside the Moon, has its skeptics. Some argue the Moon's small size and slow rotation make it an unlikely candidate for sustaining a dynamo as powerful as Earth's. Could something else have jump-started this magnetic engine, or was it all an illusion? On the flip side, proponents of the dynamo theory point to magnetized lunar rocks as undeniable proof. These ancient relics, they say, lock in signatures of a global field that only a molten core could produce. But critics fire back. Maybe those rocks were magnetized by massive asteroid impacts instead. After all, a colossal collision could have superheated the Moon's crust, briefly creating localized magnetic fields without a dynamo. It's a cosmic tug-of-war, with each side marshalling evidence from moon rocks, computer models, and even comparisons to other planets. Then there's the wild card, tidal forces from Earth. Some scientists propose that our planet's gravitational pull might have stirred the Moon's core like a spoon in coffee, kickstarting a temporary dynamo. Others counter that tidal heating alone couldn't sustain a field for hundreds of millions of years. The debate gets even livelier when lunar swirls, those eerie bright patterns linked to magnetic anomalies, enter the picture. Are they the ghosts of ancient magnetism or the result of solar wind bouncing off magnetic shields? What's fascinating is how these disagreements drive discovery. Every contested theory pushes researchers to dig deeper, whether it's simulating the Moon's core in supercomputers or designing new missions to probe magnetic hotspots. The lack of consensus isn't a weakness, it's science in action, a reminder that some of the universe's biggest puzzles demand bold ideas and healthy skepticism. Up next, we'll explore another layer of lunar intrigue, unexplained phenomena that might hold missing clues to this magnetic enigma. But the Moon's magnetic field isn't the only enigma keeping scientists up at night. Beyond those swirling magnetic anomalies, our lunar companion hides a catalogue of bizarre, fleeting events that defy easy explanation. Take transient lunar phenomena, brief flashes of light or strange glows that appear and vanish without warning. Some last mere seconds, while others linger for hours, painting the moon's surface with unexplained brilliance. What's intriguing is how these flickers often overlap with regions of magnetic anomalies. Could there be a connection? One theory suggests that trapped pockets of gas beneath the surface, agitated by magnetic fields, might burst through the crust, creating these fleeting illuminations. Others speculate that electrostatic charges, built up by solar wind interacting with magnetic shields, could spark sudden discharges. Then there's the wilder idea that moonquakes triggered by tidal forces from Earth might release trapped gases or even stir up electrically charged dust, creating these ghostly lights. But the mysteries don't stop there. Some areas of the moon exhibit temporary darkening, as if patches of the surface briefly absorb more sunlight. Again, magnetic hotspots seem to play a role, raising questions about whether invisible forces are altering the properties of lunar soil in real time. Even the temperature behaves oddly in these zones, with certain spots inexplicably heating up or cooling down without clear cause. What ties all this together? Scientists are still piecing it out, but one thing's certain: the moon's magnetic quirks and these transient events might be threads of the same cosmic tapestry. Unraveling one could shed light on the other, whether it's gases escaping through magnetic gates or hidden electrical currents weaving strange patterns across the lunarscape. And just when you think the puzzle can't get any deeper, another layer emerges. Up next, we'll tackle how public misconceptions about the moon's magnetism often cloud the real science, and why separating fact from fiction matters more than ever. Now, let's clear up some confusion swirling around the moon's magnetic field, because myths and misunderstandings often overshadow the real science. One of the biggest misconceptions: the idea that the moon's magnetic field disappeared overnight. In reality, it didn't vanish like a light switch being flipped. Instead, it faded over billions of years as the moon's core cooled and its dynamo sputtered out. Another common myth is that the moon's magnetic anomalies are strong enough to deflect solar radiation like Earth's field does. While these patches are fascinating, they're nowhere near powerful enough to shield astronauts or equipment. At best, they might slightly alter how solar wind particles interact with the surface, but calling them protective shields is a stretch. Then there's the claim that lunar swirls, those bright, curly patterns on the surface, are direct proof of a hidden global magnetic field. Not quite. These swirls are linked to localized magnetism, likely from ancient impacts or leftover magnetized rocks. They're clues, not confirmation of some grand, active magnetic system. And let's not forget the wilder theories, like the moon's magnetism being artificial or tied to alien technology. While it's fun to speculate, the truth is far more grounded. The moon's magnetic history is a natural puzzle, shaped by cosmic collisions, molten metal churning in its core, and eons of solar wind bombardment. The bottom line, separating fact from fiction, isn't just about accuracy, it's about appreciating the real wonders of lunar science. Because the moon's magnetic story, even without the myths, is strange and spectacular enough on its own. And speaking of stories, next we'll explore how this cosmic mystery isn't just for scientists, it's inspiring classrooms and museums worldwide, turning the moon's magnetism into a gateway for learning. Now, let's step into classrooms and museums, where the moon's magnetic mystery isn't just a scientific puzzle, it's a powerful teaching tool. Educators are using this cosmic enigma to spark curiosity and sharpen critical thinking skills. Picture a group of students huddled around a model of the moon, its surface dotted with tiny magnets to mimic those puzzling anomalies. Teachers guide them through hands-on experiments, asking questions like, why do some rocks stay magnetized while others don't? Or, how could something as small as an asteroid impact leave such a lasting magnetic fingerprint? These aren't just lessons in planetary science, they're exercises in piecing together clues. Much like real researchers do, museums are getting creative too. Interactive exhibits let visitors map magnetic fields on a lunar surface display, turning abstract concepts into something tangible. Planetariums weave the moon's magnetic story into dazzling shows, linking it to broader themes like Earth's own magnetic field or the dynamos of distant exoplanets. Even younger kids get involved with activities like crafting their own moon rocks, using magnetized paint, a playful way to introduce the idea that magnetism can be frozen in time. But the real magic happens when these lessons go beyond facts. By grappling with unanswered questions like why Lunar Gamma's swirls are so bright or how the moon's core once churned, students learn that science isn't just about memorizing answers. It's about asking better questions, and that's a skill that extends far beyond the classroom, whether they're analyzing climate data or debunking online myths. Up next, we'll see how this scientific saga isn't confined to labs and textbooks. It's also woven into the stories and art of cultures across the globe, proving that the moon's magnetism captivates more than just scientists. Now, let's journey beyond the science and into the realm of stories and symbols, where the moon's magnetic mysteries have sparked imaginations for centuries. Long before modern telescopes or Apollo missions, cultures around the world wove tales about the moon's strange glow, its markings, and its power, often hinting at forces we now recognize as magnetism. Take the ancient Greeks, for instance. They believed the moon's surface was marked by the goddess Artemis's silver chariot tracks, a poetic echo of the swirling patterns we now link to magnetic anomalies. Meanwhile, indigenous Australian legends described the moon as a place where ancestral spirits left behind glowing trails, strikingly similar to the bright lunar swirls scientists still struggle to explain. Even in Norse mythology, the moon's eerie radiance was tied to the god Mani, who pulled it across the sky with an invisible force, much like magnetism tugging at unseen currents. Artists, too, have been captivated. Renaissance painters often depicted the moon with an otherworldly sheen, as if sensing its hidden energy. Fast forward to modern sci-fi, and you'll find lunar magnetism fueling plots, from alien artifacts in 2001, A Space Odyssey, to magnetic storms in The Expanse. These creative interpretations aren't just fiction, they reflect humanity's instinct to personify the unknown. And here's the beautiful part, these cultural threads aren't just relics of the past. Today, poets and musicians draw inspiration from lunar magnetism, crafting works that blend science with wonder. A sculptor might shape metal into swirling forms mimicking Lunar Gamma, while a novelist spins a tale about astronauts uncovering magnetic secrets in ancient moon dust. What ties it all together? Whether through myth or modern art, people have always sensed there's something extraordinary about the moon's hidden forces. And as science unravels more of its magnetic puzzles, one thing's certain: our stories about it are far from over. Up next, we'll confront a pressing question. As we return to the moon, how do we balance exploration with preserving these magnetic mysteries for future generations? Now, let's pause for a moment and consider a question that's as important as it is urgent. As humanity sets its sights on returning to the moon, with plans for bases, mining, and even tourism, what happens to the very magnetic anomalies that make it such a scientific treasure? Think of it like this. Imagine stumbling upon an ancient library, only to realize its fragile scrolls hold secrets about our planet's past. Would we tear through them carelessly or handle them with precision and respect? That's the dilemma we face with the moon's magnetic hotspots. These aren't just curiosities, they're time capsules preserving clues about the early solar system, Earth's own magnetic history, and even the potential for life beyond our planet. Already, missions like Lunar Vertex are targeting these sites, drilling into swirls like Lunar Gamma to decode their magnetism. But here's the catch. Commercial ventures eye the same regions for resources, from water ice to rare metals. The risk: irreversible damage. A single rover's tracks or a mining operation could erase magnetic signatures billions of years in the making. This isn't just about science versus profit, though. It's about foresight. The moon has no atmosphere to shield it from contamination, no natural processes to heal human interference. Unlike Earth, where forests regrow and rivers cleanse, lunar scars and lost data could be permanent. So, what's the solution? Some propose magnetic preserves, zones off limits to development, much like protected ecosystems on Earth. Others advocate for international agreements, ensuring all nations and corporations follow strict research guidelines. Even artists and ethicists are joining the conversation, asking how we honor the moon not just as a resource but as a shared heritage. The clock is ticking. With every new mission announced, the stakes grow higher. Will we prioritize short-term gains or safeguard these puzzles for generations of scientists and dreamers yet to come? The choice we make now will echo far beyond our lifetime, written not just in policy but in the very dust of the moon itself. Next, we'll turn the spotlight to you. What role should humanity play as we step into this new lunar era? Share your thoughts below, because this isn't just a scientific debate. It's a conversation about who we are and what legacy we'll leave among the stars. Now, let's bring this cosmic mystery closer to home, because the moon's magnetic field isn't just a puzzle for scientists. It's a riddle we can all ponder. Picture this: you're holding a piece of the moon's story in your hands, a clue buried in those swirling magnetic anomalies or hidden within ancient lunar rocks. What do you think happened? Maybe you've got a theory that's entirely your own. Could the moon's magnetic field have flickered back to life during a colossal impact? Or perhaps it never fully vanished, just retreated into the shadows of its crust. Some even wonder if extraterrestrial forces like a passing comet left their mark. The beauty of science is that every idea, no matter how bold, starts a conversation. So here's your invitation. Drop your thoughts in the comments below. What's your take on the moon's magnetic secrets? A forgotten dynamo, an impact's echo, or something no one's imagined yet? This isn't just about right answers. It's about the thrill of asking questions that even rockets and rovers haven't solved. And who knows, your theory might just inspire the next big mission, or at least spark a debate that lights up the comment section. After all, the moon's mysteries belong to all of us. Let's keep the curiosity alive. So where does this leave us in unraveling the moon's magnetic secrets? From ancient dynamos buried in its core to the lingering whispers of magnetism in lunar rocks, every clue deepens the mystery rather than solves it. Those swirling patterns on the surface, the baffling Lunar Gamma anomaly, even the way the solar wind dances with the moon's faint magnetic patches, they all hint at a story we've only begun to read. What makes this puzzle so thrilling isn't just the science, it's the sheer audacity of the questions. How could something as small as the moon once boast a magnetic field rivaling Earth's? Why did it fade, leaving behind only ghostly traces? Every mission, from Apollo's rock samples to Artemis's high-resolution maps, adds another piece to the puzzle, and yet the full picture stays just out of reach. But here's the best part. The next chapter is being written right now, with lunar rovers drilling into magnetic hotspots and supercomputers simulating the moon's molten past. We're closer than ever to cracking the case. And you've got a front row seat to the discovery. If space mysteries like this light up your curiosity, don't miss what's coming next. Hit that subscribe button and tap the bell, because the moon's magnetic enigma is far from over, and neither are the mind-bending revelations we'll share on this channel. Until then, keep looking up and wondering.